So, there's one out there right now called Kepler, named after. Too much chatter going on. Johannes Kepler, who was the first guy to kind of pay attention to the planet's motion and came up with a couple formulas and laws about their motion. And they're not circular, remember. They're elliptical, yeah. And Earth's is really, really, really close to being a nice circle, but it's not. It's an ellipse. It only has to vary by a tiny little bit. Now this thing was launched in 2009, and it was a fairly inexpensive project. 600 million. Yeah. Not bad. And so far, it has discovered, like every day this number's going up, thousands of planets in other places. By the way, these are the notes not in the book, right? You got the sheet, my handout? Has discovered, thank you. You gonna memorize this, Matt, or you're gonna write it down? Thousands of planets. Recently, and I mean really, really recently, many could, my writing's not too good this Monday morning, many could sustain life. Now, how do they know that? There's a number of factors why we live on this thing we call Earth. Planets can't be too big because then they suck in and hold too much atmosphere. I looked it up. They can't be too small, otherwise they don't have enough gravity to hold the atmosphere. Okay, and based on its size in that terms, it's also determined on how far away from the sun it is, because it can't be too close, it'd be too hot, therefore it'll burn up the atmosphere, and other reasons. Can't be too far away, it's too cold, so it's like the Goldilocks planet. It's just right, right? Not too big, not too small. It must contain water. Now, just because you see a planet and you know it's the same size and everything doesn't mean you know if there's water on there or not. So, of course, it'd be really, really hard to test. Rocky terrains, okay? They just found this out. And this, by the way, this is the Kepler, well, this is what they named one of the planets that is very much like Earth. And therefore, this thing could have life on it right now. They just did this, like seriously, a couple of weeks ago. They found a cluster of about 7 planets. Where? In the Cygnus constellation. Why couldn't they have life? Like, why not? Who says we're the only one? Right? So, I'm not going to write too much about it. But maybe in a couple years, we could have a field trip. And they are 470 light years away. So we're going to have to get, like, a better school bus. A magic school bus. So some of you know what this means, 470 light years, and maybe some of you don't. We're going to have to know the definition of it. What does it mean? Shelby, pay attention. What's a light year, Shelby? Then you might want to be listening. 1 light year. If we travel the speed of light, which is pretty fast. Like how fast? 3 times 10 to the 8 meters a second in space for a whole year, That's 1 light year. So it's not a time. I know it says year there. It is a distance. Okay? It is how far you go if you travel at, what's c? It's a constant for the speed of light in a vacuum, as you found out on your last test formula, if you got that question right. How far you go if you travel at c for 1 year. So you think that's like pretty far? Well, on your first question on your assignment page I'm going to give you, you're going to find out how far in meters. Okay, so this is if you traveled at, if we had something that went the speed of light, and if you remember the little video I kind of showed you on Friday, what happens as far as the person inside the ship's concerned if he travels at the speed of light? With time. It stands still. The faster you go, the slower the time is. And I'll show you that video again, don't worry about it. Okay? But as far as he's concerned, time absolutely stands still. Now, I guess you can argue if you go faster than the speed of light, then time would actually reverse, go back the other way around. Okay, well don't worry, we don't even know how we can get to the speed of light. But if we could, and we lived 470 years, that's Earth time. So the guy in the ship, actually, that would be an instant, because time would stand still, wouldn't it? So he would just get there. And he wouldn't be any older, per se. But according to someone on Earth, now, I mean, that's 5 generations have died since the time it took for just to leave here and get there, right? So that's quite far away. Does anyone have a question of how they actually could see that? It's not a telescope. We know that because as we're looking out in this area, you know, like stars twinkle because the light comes through the atmosphere and kind of bends back and forth, and that's why it looks like it twinkles, right? Because it gets moments of higher and lower intensity. But what we do is they actually look out this way, and then they notice that this star is there, and all of a sudden it disappears. And then it's there again. And it might disappear for 10 minutes, it might disappear for an hour. Well, how does that happen? Something must cross in its path, right? If I stood here with a flashlight and somebody walked in front of it, well, then all of a sudden you wouldn't see the flashlight. So we know that it must have been a planet that went in front of that star. And then these complicated formulas, they can figure out, well, then there's another one, okay? So that's how they kind of know. And then they can actually, based on how long it took, they, I guess, determine the size. This is beyond me, right? I'm just kind of pulling at strings here. But that's how they kind of tell, because that's an awful long way away. You can't see that with a telescope. So anyway, this is how far. Now remember your formula. D is a distance, how far. If I know a speed and I know a time, I can figure out a distance. Well, what's the speed we're talking about here? 3 times 10 to the 8, that's meters per second. And if I multiply that by a time, then I get a distance. But remember, these units don't cancel, do they? So all you have to do is find out, well, how many seconds are in 1 year? That'll cancel out, and then I'll be in meters. Okay, but I'm not going to do that for you. That's your first question on your assignment. Okay? Light year is a distance. A very, very, very far distance. Okay. Time dilation. What does dilating your pupils mean? Bigger. Yeah. So this is like stretching your pupils. Make them wider, maybe make them smaller. Well, it doesn't make any sense for us at this point, until we get to physics 11, to even think that time can be larger or smaller. But it can. So here's a little experiment that these guys did. This is from Mr. Gore's other book. It looks the same in yours, but it is from a different printing before this thing was printed. So there was 2 things. This guy came up with, okay, some Mr. McGoldrick would be really happy because he's Scottish. A theory of electromagnetic radiation, and he predicted the speed of light would be about 3 times 10 to the 8 meters a second. That's in kilometers, right? All right. So a couple guys came along later and said, well, let's kind of find out and let's kind of prove it. But while we're at it, they all thought that space was this ether. Because at the time, remember the argument that light is a wave or a particle? They thought it was a wave. But the light comes from that star to us, so it must have some medium to permeate through, right? Because again, we said that in space you can't really hear someone's sound when they speak, because that wave has nothing to vibrate against. There's nothing there. So they thought there was this ether out here in space, because that's the only way that light could vibrate to us, right? But they also thought this ether was this fixed frame of reference. We've been talking about frames of reference. And you know, we're moving on the Earth's moving around the sun, and this is all moving too. Well, there's got to be some absolute frame of reference where everything can be based, their speed can be based and relative to. So they tried to set up this experiment to try to figure out this ether, right? So here's what they did. They know the light from a star, speed c, is coming in. So right here, if this is our planet and I'm moving in this direction, then that should be like if I'm got radar on a car coming towards me and I walk sideways, my motion's not going to affect that speed that radar is going to pick the car up with, right? If it's coming towards you at 100 kilometers an hour, that's what radar means, right? With Doppler effect, that's 100 kilometers an hour. If I go sideways, it should be the same thing. Now, in January, as the Earth is moving towards it, if I start walking towards that car at 100 kilometers an hour, this radar reading should be higher, right? Like if this car is coming at me at 100, that's the light from space, and if I go towards it at 100, then as far as my radar is concerned, it's like the car coming towards me at 200, right? You okay with that? So I'm moving at 100 closer to it, and it's coming at me. Is that okay? And then, so they took a reading, okay? 6 months later, or 7 months, they took another reading. So this is still coming in. Let's think of it as a car, not the speed of light, because then the number's more manageable. And if I move away from this car at 100, it's coming towards me, I'm going away from it at the same speed, and I take radar, then what's my radar going to read? It's going to be 0, isn't it? As far as this is concerned, there should be no speed, right? So what they tried to do was just find the difference and then try to figure out, you know, what this ether stuff was. So what happened? This experiment is famous for its negative result. They found that they got exactly the same speed. And yes, this is only less than 100 years ago. Okay? They found out they didn't get any difference at all in these two speeds. Okay, does that make any sense? This speed, when they went towards it, was some value, came out to 3 times 10 to the 8. And then as they're moving away from it, it still came out as exactly the same speed. And they shook their heads and went, this doesn't make any sense at all. So they did another experiment, same thing. Some other people tried to do the same experiment, same result. But when, you know what, Einstein hadn't got a clue that they were doing this, and the speed of light is c, which is 3 times 10 to the 8 meters a second. Okay, but most of us know that already. He actually predicted this. Okay? The speed was the same whether Earth moved toward it or away from it. And this is our second postulate of special relativity. Okay? The speed of light does not depend on your frame of reference at all. So if you move towards light at the speed of light, it still looks like light's coming to you at the speed of light. And if you move away from light at the speed of light, it still comes to you at the speed of light. Its speed does not change. It makes no sense at all, but it's true. So, the second postulate, let's write down what I just said. Light, or C, travels at constant speed. We take as C in space or anywhere else, independent of the speed of the observer or the source of the light. And you can word this lots of different ways, but that's how I got it worded. Okay, it doesn't change. Remember that. True-false questions. Multiple choice on the test. C is C. Doesn't change. Whether you go towards it, away from it, it's still C. All right? What if light is not in space? Well, you know from our last test, okay, it does slow down through different, we call them mediums, but you can think of it as substances. When it's got nothing to hit, it moves at 3 times 10 to the 8. But we've done problems, right? It slows down and doesn't go quite as fast if it goes through glass or through water or through some other transparent medium where I can actually get through. Okay? So C only means in a vacuum. And I said that before, let's say it again. Okay, let's get to the really weird stuff. I'm not going to explain all this, but if you're curious where they kind of, when I say they, Einstein, derived this formula, and we showed you a video on this, according to him, the light that bounces down to a mirror and comes back goes over some distance. But according to this person, as the ship is moving, it goes a lot farther. And because the speed of light is constant, then that all changes as far as the distance, and therefore the time changes. That's the time dilation, and here is the formula. Okay? So I'm not going to run through it and prove it, but there it is. This is on the back of your book. Okay, looks exactly the same, only they don't have the fraction written horizontally, they got the fraction vertically. So, what does this mean? We have to come to sense with the fact that there's 2 different times. Okay, time is not a constant anymore. Time is dilated based on how fast you go. And did they actually prove this after Einstein came up with it? They did. They got a super, super precise clock, like accurate to the, I don't know exactly, but say 100,000th of a second. They had 2 identical clocks, okay? Made in Switzerland, where they make all the good stuff. They synchronized them. One they kept right here on Earth, the other one they set in the fastest jet they had at the time. And they flew it around for a few hours and brought it back, and they went click, and sure enough, the one that was on the jet was a couple 100,000 seconds slower than the one they kept here. Okay? So, what does this formula say? Note that when we're doing a problem, and just looking at this example, usually when we give you distance or speeds is what I'm trying to say, we don't give it to you as a number. You know the speed of light 3 times 10 to the 8, but usually it's always a fraction of c. This is a half a c. You want that because in the formula you got c squared. So if you put in half of c, that's velocity, and you square it, what happens with c squared over c squared? Yes, and you want that. So don't put it in as, well, half a c is 1/2 times 3 times 10 to the 8, which is 1.5 times 10 to the 8, and then divide that by 3 times 10 to the 8 and square it all. You don't need to. Okay? All you got to put in here is 0.5 squared, which is 0.25. Okay? So according to this, that's 15% bigger or stretched by 15%, which means someone on Earth, time is 15% longer than someone in the spaceship if they traveled at half the speed of light. So the C's cancel. Maybe, usually, there's no need to put that in the formula, okay? Now the tricky part with this is which time is which. Memorize this. The time in the ship is T-O, okay? That's the ship. When I say ship, that's the that's the clock that's moving. Moving clocks run slower. I'll write that in a sec too, okay? You got to memorize that. This is the person on I'm going to say Earth, but it might not be Earth. It's the person that's not moving. Usually the questions say someone on Earth, someone in a spaceship, okay? 2 different times. Time to stationary observer is T. And you should know if you get it backwards, because it shouldn't make any sense. But if you just memorize moving clocks run slow, I guess if I was an English teacher it would say more slowly, but I don't care. Okay, time in the ship is always going to be less than fixed observer on Earth time, or wherever that person is not moving. Fixed. Okay? So I just have one example. Should be enough. Example. A 30-year-old travels at the speed of, what does this say? 0.99 times the speed of light, or 99% of the speed of light. Okay? We can't do that yet, but who knows? Maybe by your birthday. 5 years. Which time is this? Is it T or T naught? Is that ship time or is that stationary observer time? That's the guy on the ship is traveling for 5 years, okay? That's his time. Keep reading. How old will his 6-year-old daughter be when he gets back? Well, how much time will elapse on Earth? As far as she's concerned, as far as a fixed observer is concerned, what is T? Okay? So there's the moving time, 5 years, and then there's a fixed time. That's what we're trying to figure out. So this is the easiest thing to solve in this formula. How many variables are in this guy? 1, 2, C is a constant. That's 3 times 10 to the 8. The hardest thing to do is to solve this thing for V. And yes, I'm going to make you do it. Okay? So first, T is T naught. I'm also say that now before some professor says it, TRU, and you go, what? That's what they say. I don't know why. 1 minus V squared over C squared. I'm trying to find T. I know the time on the spaceship, according to the traveling guy, 30-year-old is 5 years, and the velocity is 0.99 c. Put that in for v, and that's over c squared. Okay? Only one variable here, and it's solved for that variable. So first, you remember exponents, this applies to everything in the brackets, right? So I'm going to rewrite this just to show you, and then after that you can kind of take some shortcuts. That's 0.99 squared times c squared all over c squared. Now, like I said, don't make 0.99 times it by 3 times 10 to the 8 and make it a big ugly number that you're going to round and then not get the right answer because you rounded it. Because what happens with the c squareds? They're gone. Okay? So now I just have 1 minus 0.99 squared on the bottom. Take the square root of it. Okay, so I'll write that. What's all that stuff on the bottom? Well, 1 minus 0.99 squared is that. I want to take the square root of that, but let's write that out. Square root of the answer is that thing. And how many times does that thing go into 5? Okay, weird way of doing it, but some of you guys, why didn't you ever show me that before? Well, here, I showed you it again. Okay, so T is 35.4, but what is the question asking? How old's the 6-year-old daughter? So her age, when he gets back, is 35 and 6, or 41.4. How old is the traveler when he gets back? He is 35. So when he gets back, his daughter is older than he is. Okay, that's time dilation. That will happen. It's been proven. We just can't travel that fast yet. Okay? But forget about all the beauty creams out there that are thousands of dollars. Just build a fast spaceship and then, you know, keep you looking young forever and ever and ever. Okay. You're going to do the worksheet. Do you want me to show you now how you solve this thing for V, or wait till you do the question? Let's just start doing some of these first.